Okay, so what I want to talk about is a final pattern, which is a final form of recursion that's called backtracking. There are many wonderful algorithms in computer science, and often using recursion to understand how those algorithms work can be incredibly helpful. So the backtracking pattern is a common recursive pattern that gets used to solve all kinds of different problems. So I'm going to give you just a simple problem of doing a tree traversal. And what we're doing with the tree traversal is we're trying to get to the leaf nodes to find out if we can have a leaf node that is a good leaf node. All right, so let's consider this tree. Whoops. We're going to start out with root. There's the root of the tree. That branches to a node A and a node B. A branches to C and D. B branches to E and F. And some of these leaf nodes, C, D, E, and F, some of them are good and some of them are bad. So I'm going to mark the ones that are good and bad. So C, D, and F, those are bad leaf nodes. All right. And E, that's a good leaf node. So what we'd like to do is, starting at the root, we'd like to find one good leaf node and then stop the processing of this tree. So our goal is to search the tree to find a good leaf node. So we can do this in a recursive way. And so I'll just describe how we would do it recursively, and then we'll work on a solution to get us to a place where we can solve the problem. Okay, so we're going to start at the root. And the root has several children. So we're going to process each of those children. All right, so we have a list, and we need to go through every item in the list to process it. All right, so you can think there's probably a recursive way to go through items in a list. Of course there's a recursive way of doing that. Okay, so the first child in the list is A. The first question I would ask is A a leaf node? And the answer is no. Okay, it's not a leaf node, no problem. So what we want to do then is we want to go recursively from A to its children and see if any of those are leaf nodes. So A has two children, C and D. And the question is, are they leaf nodes? So let's go through each child and we'll figure it out. Is C a leaf node? Yes, it is. Is it a good leaf node? The answer to that is, yeah, it is. No, it's not. So we're going to ignore C. All right, does A have any other children? Yep. D. Is D a leaf node? Yep, it is. Is it a good leaf node? No, it's not. All right. Does A have any more children? No. Okay. So that means we're done processing A and we didn't find anything good. So we're going to return back to the root and we're going to see if the root has any more children, which it does. So B is a child of root. So we're going to start exploring B. Is B a leaf node? No, it's not. All right. Let's look at the children of B. That's E and F. All right, the first child of B is E. Is that a leaf node? Yes, it is. Is it a good leaf node? Why, yes, it is. Okay, so that means that we found a good leaf node under B's children, which means that B can return to root and say, yep, I found a good leaf node and it is B. And we're done with the processing. So you can see there's several levels of recursion here, right? There's a recursive traversal of the tree. This is a simple tree. It only has 3 levels, but you can imagine a tree that has many more levels. And then also, there's a recursive processing of the children of any particular node in the tree. All right. So we're going to work on the code to make that work. Okay. Well, let's, we're switching to some code so we can try to get some things to work. So first, what I'd like to do is I'd like to try to define a tree. So let's define a tree. We'll call it sample tree. And we'll make it work like this. If you're a node in the tree, you just show up as an atom like that. And if you have any children, they just follow you after that, after you show up. So there's A, and then the children of A, I'm sorry, there's root. Then the children of root are going to be A, well, A and B. Okay, but the thing is, A and B are both nodes that have their own children, so we're going to put that A and have A have a node C and D. And the same thing with B. B has two children, E and F. Okay. Now, if you remember from our notes, A and B are nodes that are not leaves, but C, D, and E are, and there's some indication of for C, D, and E as to which is a good leaf, or which is a bad leaf. Okay, so bad leaves are the ones in red, good leaves are the ones that are in green. There's only one of them here. Okay, so let's indicate whether something is a good leaf or a bad leaf by following the leaf node with giving each leaf node its own piece of information to indicate whether it is a good leaf or a bad leaf. So we're going to immediately follow that node with a true or false. Okay, whoops, I got a little bit crazy here because I'm not following my own rules here. So there's A, which has two children, C and D. And there's B, okay, and that takes care of A. Here's B, which has two children, E, which is false, which is true, and F, which is false. Takes care of B, that takes care of root. Okay, cool. So what we've done here is we've created a list encoding of the tree that we have right here. Let's see if I can put one below the other. Huh. All right, so we've got a scheme encoding of the tree. There's the root. All right, that's the first element in the list, followed by its two children, A and B. So there's A and B. A has two children, C and D. So there's A followed by C and D. B has two children, followed by E and F, its two children. And each of the children has an indicator as to whether, if it's a leaf, as an indicator as to whether it is a good leaf or a bad leaf. So false means it's a bad leaf, and true, E is true, means it's a good leaf. Okay, cool. So why don't we write just a couple really simple methods to mess around with this tree? All right, one thing I'd like to do is I'd like to write a method called getChildren. And all getChildren does is it just gets the children of the tree. And that should be rest tree. Let's test it out. All right. All right, let's get the getChildren of sample tree. Okay, that looks pretty good, right? A and B are the two children. Okay. Now, the other thing that would be interesting to know is, do we have, is a particular child a leaf node? So is leaf. Okay, is something a leaf? So what does it mean to be a leaf? Well, let's take a look at C. C is an example of a leaf. First of all, you have to be a list. You're not a leaf if you're not a list. All right, so let's make an and. Are you a list? Child, are you a list? All right. Secondly, what we should see is the second element in the list should be a true or a false. So first of all, you have to have a second element in the list. I guess that's a good thing to check, right? So, is the second element, if we remove, let's think about this. So if we say rest, let's create, let's go down here and just do an experiment. So we'll just run this. There's an error. That's okay. Let's do an experiment down here to play around with. So let's say we have our C false. All right, so that's the thing that we're going to process. So we want to figure out if there's, first of all, it is okay to ask for a second. Well, first of all, is the list empty? So let's do that. So let's try a couple experiments. So is the list empty? And we'll do C false. Okay, so we don't want the list to be empty. In fact, what we're interested to know is if we remove that first element from the list, is the list empty? I guess we're being really paranoid because I don't want to get something and create an error. So if we remove the empty, if we remove the first, so it's a list. Okay, so is the rest of the, is the rest of C false? Is the rest of C empty? So that needs to be false. So let's make that, let's just look at what is rest of C. So rest C false. That's going to be a list containing false. So we basically said, we're looking up here and we're saying, is child, which is C false, is that a list? Okay, so this is a list for sure. Now, if I extract if I get rid of C, basically, and is that empty? That's what this is saying. So if it is empty, then we have a problem. So I want to say, is it not empty? So really my expression needs to be not empty, C false. Okay, so this will remove the C and ask the question, is the list that we're left over with, which is just going to contain false, is that not empty? All right, so let's get that in here. Take that and move that up here. Okay, we don't have to say rest C false because we can say rest child. Okay. All right. Now we have to figure out whether we have the value that's there. I mean, it could be a list of nodes, and that's not good. We need this to be true or false. So we can use equal here. So we can say, all right, is the first of the, I think it's going to be first of the rest of the child. Let's see. So let's take this, see false. We need to extract that false, basically. That value that's it's either going to be true or false. So I think we can say first. Yeah. Okay. Is the first of the rest of the child, is that equal to true? All right. It's either going to be true or false. And so we'll make that an or. So we're saying if we're passing in C false, is that a list? Yep, better be a list. If we extract the C, do we still, do we have a not empty list? That's important. That'll leave us with just false, a list containing just false. And is the thing that the first thing in the list when you extract the C, is that true or is that false? Okay, so that will define whether something is a leaf, and we can test it, right? And I just want to review what we have here. So that's an example of a leaf. It has to be a list. The second element in the list, if we remove the first element in the list can't be empty. That's what this says. And the second element in the list has to be either true or false. That makes it a leaf. Okay, so let's test it. All right, so we'll run this. And then we'll say, let's see, we don't have to write all that. We can just say, is leaf C false? Ooh, it says it's false. Let's see if we can figure this out. So, is equal first rest child. True. We'll say false. And first rest child, child's going to be C false. Oops. Oops. Okay. I can fix that. All right, let's look at first rest false. Because it doesn't think that they're equal, so there must be something I'm doing wrong here. Oh, I have to say quote false. Right, because I'm treating it like an atom. So now if I do, so I'll show you what I mean here. That's why it's not working. There we go. Okay, so the only problem here is I can't say just true. I have to say quote true and quote false, because as far as the language is concerned, these are atoms and not the value true and the value false. Okay, maybe I have too many parens there. Nope. Oh, I have a, this is the problem. Okay, there we go. Nice. Okay, so let's try isLeaf again. C false. Whoops. isLeaf. C false. All right, that's true. Let's try isLeaf D true. Not sure how that quote got added there, but okay, perfect. Let's try isLeaf, and we'll try, let's try this whole thing. isLeaf sample tree. And let's try one more. We'll try this. Just have to put a quote in front here. Good. All right. So yeah, with some limited testing, it looks like isLeaf works. Now we also want to know if it's a good leaf. All right. So we're going to create another method called define isGoodLeaf. So I haven't written anything recursive yet. What I'm working on is kind of like helper methods that are going to help me think about how this should work. I'm definitely going to need to be able to get the children of a node that I'm at. I definitely need like sample data to work with, and it definitely see that there's going to be a need to know whether I'm working with a leaf node or not, and also whether a leaf node is good or not. Now the only difference here is that we need to make sure that it's a leaf. So I can just say is leaf child. So we need that. And then the other thing that has to be true is the child has to be a leaf, and it has to have the value of true in the leaf. Okay, so I think that's pretty good. So that gives me whether a leaf node is good or not. And now I can try is good leaf C false. Nope, that's not a good leaf. Is good leaf E true. And that is a good leaf. Okay, cool. So now I've got the ability, I have a tree. I can get the children of a tree. I can get whether a child is a leaf node or not, and I can get whether a child is good or not. So now what I can do is start to work on the heart of this, the sort of recursive backtracking tool method. And I'm going to make it look like it was just so easy to just write this down. I'm writing at the top of my head, but that's not true. I actually worked before the lecture. I wanted to make sure that I had a working method that would make a lot of sense, and think about the sort of thought process that would go on to decide how this should work. So I'm going to jump back and forth as I explain this using using the diagram that we started out with. All right. So let's look at that diagram for a second. So let's think about a real easy case. All right. So I'm gonna do this. I'm going to say that we're gonna have a method that's called backtrack. All right. So we're gonna define that. Define backtrack. And backtrack takes a tree. And the way backtrack works is it says, is there any child that I have that's good? and I'm going to pass it in get children from the tree. All right. So what does that mean? Well, when I call is any child good, what that's going to do is it's going to look at the children of, it's going to look at my children. So if I'm root, when I call get children, it's going to return A and B. And of course, included with A and B are C and D and E and F. They're part of that. If you look over here and we think about it in terms of our representation of the tree, when I say get children and I'm starting with root, I'm going to get the list that contains A and all its stuff and B and all its stuff. All right. Okay. Now what we have to determine is with this method, is any child good? And that's really the heart of this program. Is, let's write define is any child good? And we're going to pass. So that is going to, what's being passed into that are children. So we have to move through this list of children and figure out if any of them are good. So the way that we're going to know whether a child is good or not is it's a good leaf node, or there's a leaf node under it that's good. And if neither of those are true, we need to move on to the next child in this list of children. Does that make sense? All right, so let's do that. So first of all, is this a good leaf node? All right, so let's put our buddy Cond up here. Cond! And we're going to say, is this a good leaf node? So, and is leaf. And what we need to do is we need to get the first child. All right. So the first child in the list of children is going to be the first children. All right. So if we go back up here, the first child in the list of children under root is going to be this entire big list. All right. But if we look under A, if we're considering A and A's children, we're going to do this recursively anyway. The first child under the A is going to be the C false, which is a leaf. Okay, so the first question we need to ask is this a leaf? And the second thing we need to ask is this a good leaf? And we're doing it in that order because we can take advantage of short circuit evaluation, and we're not going to check to see if the child is a good leaf if it's not a leaf. So this will get checked first, then this will get checked. Okay. So if that and is true, if both of those are true, life is good. It means we're going to return true. We've got goodness. In fact, I think I'm going to actually do this. I'm going to separate the cond from this test, and I'm going to write right here, this is the first child is a good leaf. What that means is return true and stop backtracking. Basically, just stop backtracking. And recursion. We're done. Okay? All right. Now, the other thing that's a possibility is that the first child is a bad leaf. All right? So that situation, so it's not a good leaf. So when we have that situation, we don't want to return false. Let's take a look at y. It's tempting to return false, and actually the first time I wrote this I did return false, but let's take a look up here. So if the first child is a leaf, but it's not a good leaf, then what do we want to do? We want to plug in our computer. That's what we want to do. Okay, other than plug in our computer, what do we want to do? Well, what we want to do is we want to return, we want to check the next child, all right, and see if that one's okay. So if we're going to check the next child, then what we need to do here is we need to call is any child good with the rest of the children in the list. All right. Let's see, I might be able to make this a little bit smaller so it's visible. There we go. That's better. Okay. So when we call is any child good with the rest of the children in the list, what that's going to do, if we look up here and we consider the case where we're processing A's children, first, that's a leaf, but it's not a good leaf. So what we're going to do is we're going to check is any child with anything else that's left in this list of children process, and that will be D. Okay. All right. So first child is a bad leaf. And what we're going to do here is check rest of the children. Okay, so now we can deal with the case where we don't have any children. All right, in fact, I'm going to write a comment here for that. So first child is not a leaf. All right. So the first child is not a leaf. Then we're going to check for, we're going to check, what should we do if the first child is not a leaf? Well, let's see what an example of that would be. Here's root, and here's an example of a first child that's not a leaf. All right. So what we need to do is we need to check it to see if its children have any good leaves. All right, so here's root. The first child of root is this subtree, and we need to check that subtree to see if any of its children have good leaves. Sometimes they will. This is an example where one of the sub leaves or sub branches of the tree ends up having a good leaf. And sometimes it's not. All right, so if the first child is not a leaf, we want to check first child's children. All right, so let's do that. So, is any child good? Now, what are we passing into is any child good? Well, we're going to pass in the first child's children. So the first child's children are going to be get children of the first children. That's the first child's children. Okay. Now, if that returns true, that means that one of the children of the first child is a good leaf. So that means we're going to return back up the line. So a better way of saying this is first child is not a leaf, but there is but there is a good leaf below first child. That's a better way of saying it. All right. Okay. Last thing, first child has no good leaves. Okay, so that means we've checked we've checked the first child. That's what get children first children is, and we've looked at all of its subnodes and found the leaves, and we checked every leaf, and we didn't find any of them that were good. And so if that's true, if we haven't found anything good, then this will not return true, and we'll kick down into this last piece of code here. And the last piece of code, what we're going to do, oh, I should go back here for a second. So if things are good, if we're one of the subleaves of the first child, or subnodes are of the child, well, whatever, leaves of the first child, which could be several layers below. If one of those is good, we're going to return true and stop backtracking. Okay. And then finally, if we've got the first child and it has no good leaves below it, we're going to return any child good. And so first child has no good leaves below it, then we're going to check rest of children again. So it's going to be just like this right here. In fact, I can just copy and paste that and check the rest of the children. All right, that ends the cond. And now we can compile it. Okay, so the next thing we want to do is test it. So is any child good sample tree? Whoops. Let's just make sure I got that right. I think I've got that right. And it says expects a non-empty list, and it's given root. Let's run the debugger and see where the error is. Maybe we can figure this out. Okay. Is any child good? And we're going to do sample tree. Okay. So, oh, it's supposed to be rest children, not first children. Okay, so let's stop that. And actually, I was probably wrong in both places. Yeah, no, I just messed it up here. No, I think that's right, actually. Is any child good? Get children, first children. Get children tree shouldn't have passed in root. That's weird. Let's look. Oh, I see what I did. No, actually I'm a little confused here. So get children tree should not have passed in root. So, all right, let's use the debugger and see what's going on here. So what I'll do is right here, we'll say is we'll say, is any child good? And, oh, sorry, we'll say, sorry, backtrack. I think that's where I went wrong. Backtrack sample tree. I think I was saying, is any child good sample tree? And that's why it ran incorrectly. Okay. Oh, okay, so that's interesting. So I have one error, which is that first expects non-empty list given blank. And I could see a situation where, as I'm processing these lists, that I end up with a situation where I've extracted all of the children from a particular branch, and none of them, all of the leaves from a particular branch, and none of them are good. So what I'm going to do here is I'm just going to add one more case, which is we have an empty list, and this means there are no more children to process. So return false. Okay, so is the children list let's fix that, is empty children. The list passed in is empty. We're going to return false. Okay, let's try running this again. Oops, empty goes there. All right, let's try running it again. Okay, it returns true. Now, I'd say it's a little bit mystifying, right? It returned true. That means it found a good leaf. Could we get a little bit of information? Well, we can. I'm going to cheat a little bit here and put a let in just to give us some debugging information. So let x0 be the display of children. All right, so we'll print out what the value of children is as this runs. And we'll let x1 be the display of the new line character. And we will, I think you have to do another open friend here. Close that. And this is the next part of the let will be our cond. And then after our cond, we're all set. So let's let this run. Okay, so this shows the recursive processing of the tree inside any good children. So the first time we come in with this children, we have the list for root, which is this. So A and B are the two nodes that we're processing. And then we can see we're processing A's children, that's C and D. And then we're processing D, and we find the empty list. Okay. And then I don't understand why we're not processing C there. Oh, C by itself, because we're always looking at that first. When we get A's children, the first thing we do is we look at the first node in the list, and we process that. And if that turns out to be not a leaf node and its children aren't in a leaf node, then we process the next node in the list. That's what's happening here. Okay, so we process D, and then we try to process any other further children in the list of children of A, and that's an empty list. So we know that we've explored A's children, and nothing happened. So we end up backtracking, and we backtrack back to the original recursive call, which was this, and we look at the next child in the list of children for the root, and that's B. And starting with B, we look at its children, and we say, okay, well, we're going to look at the children of B, so that's E and F. And the child E is a leaf node, and it is a good leaf node. So we've achieved our goal. All right. So that explains and that is an example of using backtracking in recursion. So the key here is that you explore routes, and if you find a dead end, you back up using the stack to a place where you have more routes to explore. And if you explore more routes, eventually, hopefully, you end up finding your goal state. In this case, that's a leaf node that has the value of true. All right,